Okay, now we will summarize. Now I am going to sketch the velocity triangle. For an impulse steam turbine. What is an impulse steam turbine? In the moving blades, there will not be any pressure change. Okay. Okay. So now this is the moving blade. This is the moving blade. Along the blade direction. Along the blade direction, I have CR1 and CR2, the relative velocity vectors. So this is CR1 and this is CR2. This is the first vector that you have to draw. The second vector is the blade speed. U is the blade speed. Now I draw U here. In the inlet velocity triangle, I draw U here for convenience. In the exit velocity triangle, I draw U here. Okay, so this is U and this is U. The third step is U plus CR will give you CA. Again, CR plus U will give you CA. So the third step is to close the velocity triangle by drawing the absolute velocity vectors. So this is CA1, this is CR1, this is CA2. Are you there? Now this angle is called beta 1, this angle is called alpha 1, this angle is beta 2 and this angle is alpha 2. Okay. Now I am going to put both of these velocity triangles on the same diagram and that will be the final velocity triangle, combined velocity triangle. Now if you see what is common to both of these triangles, it is the blade speed. This is also U, this is also U. So now I will keep U as a common vector. This is U. Now I will first draw this velocity triangle in yellow. The inlet velocity triangle will be in yellow. You see the inlet velocity triangle. This is CR1 and this will be CA1. Do you agree? This is CA1 and this is CR1. Are you there? The inlet velocity triangle is like this. Now what is this angle? This angle is beta 1. This angle is alpha 1. Now let me draw the exit velocity triangles in a different color, in orange color. In the same figure I have to draw the exit triangles. So do you see that this is U, this will be CR2 and this will be CA2. Now I will draw this way. This will be CR2 and this will be CA2. Okay. CR2 is nicely inclined, this CA2 has a lesser inclination. Now this angle made by CA2, this angle is going to be called as alpha 2 and this angle is going to be called as beta 2. CR2 is going to make an angle of beta 2. Now this figure is what you have to remember. The yellow one is the inlet velocity triangle, the orange one is the exit velocity triangles. Okay. Now in this velocity triangle, the next step is to resolve CA2 and CA1. How do we resolve CA1? CA1 is resolved as, see this is CA1, its horizontal component, we call it as CW1. Right? For this whole vector, the total horizontal component, I call it as CW1 and the vertical component is going to be called as CF1. Okay, so we have resolved CA1 into CW1 and CF1. Similarly, the next vector that we have to solve is CA2. So I am going to resolve CA2 into CF2 and CW2. That's it. So this will complete the velocity triangle. Okay. So we have blade speed common, which is u. This white one is u. That is the blade speed. That is common to both the velocity triangle. Then the yellow velocity triangle is the inlet velocity triangle. The orange velocity triangle is the exit velocity triangle. Then you mark alpha 1, alpha 2, beta 1, beta 2. Finally, you resolve CA1 as CW1 and CF1. You resolve CA2 as CW2 and CF2. This will be the complete velocity triangles. You have to remember this velocity triangle. Okay. You have to memorize the velocity triangle. Now, what are the relations that we can find from the velocity triangle? Now, what will be CW1? CW1 will be, these relations you have to memorize. CW1 is the horizontal component of CA1. So, it will be CA1 cos alpha 1. CA1 itself is inclined at alpha 1. So, its horizontal component will be CA1 cos alpha 1. Its vertical component will be CA1 sin alpha 1. So, CF1 will be CA1 sin alpha 1. Is this clear? Similarly, for the exit velocity triangle, CA2 has a horizontal component of CW2 and this is inclined at alpha 2. So, CW2 will be CA2 cos alpha 2 and CF2 will be CA2 sin alpha 2. Are you with me? So, these are the relations that you have to remember from the velocity triangles. So,